Hello everybody, welcome to the 11.7 video over the ratio of areas, which is the last section we're going to be doing in chapter 11. And our goal is to find the relationship between the ratio of sides and perimeters and areas, specifically of similar polygons. And if we have similar polygons, the relationship is a little easier than if they are not. So if I take a look at this first example, I have two triangles, and I'm telling you here that they are similar because we have a similarity statement. And so what I would like you to do is I would like you to pause the video. I would like you to find these two sides using the Pythagorean theorem, and I want you to try parts A through D and see what you know first, and then I'm going to come back with my work. So please pause now. All right, so here is a lot of my work. First, when I did the Pythagorean theorem, I got that this hypotenuse was 2 root 13 for triangle number 2, I'll call it. And I got triangle number 1 to originally be the square root of 117, which 9 went into, so I made this 3 root 13. So then for part A, when it said find the area of each similar triangle, the area of triangle 1 here ended up being 27 units squared, 1/2 base times height. And then the second one, 1/2 base times height, was 12 units squared. Part B, finding the ratio of the sides, I compared 6:4 because these two triangles are similar. I know these two sides are proportional. I then reduced that to 3:2. So the ratio of the sides would be 3:2. To find the ratio of the perimeters, I would say this is the most pain part. For part C, what I ended up doing was I represented this perimeter as 6 plus 9 plus 3 root 13, and I represented this perimeter as 4 plus 6 plus 2 root 13. I then combined my like terms on top and bottom, and then noticed on the top I could take out a GCF of 3, and the bottom I could take a GCF out of 2. When I did that, what I was left with in the parentheses was the same, so I canceled it out and was left with 3:2 as well. So what's interesting so far is if you have similar triangles, if the ratio of the sides is 3:2, the ratio of the perimeter should also be 3:2. Furthermore, if you find the ratio of the areas we found in part A were 27:12. And if I reduce that, dividing by 3, I would get 9:4. And I want you to notice, if this is the ratio of your sides here, 3:2, how does the ratio of the areas compare? Well, 3 squared is 9, and 2 squared is 4. So there's an interesting connection between the perimeter, the area, and the units we've been using. So down here, to summarize, if I extend this page, if my shapes are similar, if the ratio of my sides is something like x to y, the ratio of my perimeter must be x to y also. Because if I look back up at the problem I just did, the ratio of the sides and the perimeter ended up being the exact same, which makes sense with what we've been doing, by the way. Because if these units had something like centimeters on them, your ratio for the perimeter would also just be centimeters. However, if the shapes are similar, and if you have, if the ratio of the sides is x to y again, we notice that when we found the ratio of areas, it was the sides squared. So then the ratio of your areas, you could represent as x squared is to y squared, which again makes sense with the units we've been dealing with. With perimeter, when we had centimeters for the sides, we had centimeters for the perimeter. But if we had centimeters for the sides when we're trying to find area, my unit ended up being centimeters squared. So it makes sense that my ratio of my areas would be squared to squared. But this is only true if your shapes are similar. If you don't have similar shapes, we would have to rely on the area formulas. So I'm going to write a little note. Not similar, question mark. Rely on the area formulas. I apologize about the handwriting. I'm using a different pen. It's not that great, so thank you for dealing with it. Let me get into some examples so you can see how this can be used. This first one, find the ratio of the areas of similar hexagons with corresponding sides of 22 to 12. So because my shapes are similar, if I wanted to first find the ratio of the sides, that would be 22 to 12, which could be reduced because I could take a 2 out of both, to 11 is to 6. So then if I wanted to find the ratio of the areas, which is what this question's asking for, because my shapes are similar, I can just say that the ratio of my areas is 11 squared to 6 squared, which would be 121 to 36. So that would be my answer for number 1, because the shapes are similar. If I looked at number 2, the first thing we'd have to ask ourselves is if the areas or if the triangles that we have are similar. So I'm actually going to start with part B first. If I looked at these two triangles, because these two lines are parallel, and either of these are considered a transversal, I know that these two angles must be congruent because of alternate interior, and these two angles must be congruent also because of alternate interior, and these are also congruent because of vertical angles. So I know that these two triangles are similar because of at least angle-angle. And so what I can do to find the ratio of the areas is say, I know that these are similar, so let me find the ratio of my sides first. So if I look at my shape, two sides that I could compare, if I look at how the angles are marked, is I could compare 12 is to 20. I couldn't compare 10 and 26 though, because if you look at the 10, it's between two different angles than the 26 is. So the ratio of my sides would be 12 is to 20, which would reduce to, let's see, we can divide these both by 4. That would reduce to 3 is to 5. So if that's the ratio of my sides, the ratio of my areas would be 3 squared is to 5 squared, or 9 is to 25. So 9 is to 25. Let me write that a little bit more nicely. Sorry about that. 9 is to 25 would be my answer for part B. However, in part A, I don't think there's a way that we can prove that triangle 1 and triangle 2 are similar because they have no angles in common, so I can't say angle-angle. So when I can't assume similarity, what I'm going to use instead is the area formula. If I want to find the area of triangle 1 and compare that to the area of triangle 2, I could use 1/2 base times height and 1/2 base times height. Now, in this situation, I don't know any numbers, but I do know that all of these segments are the same. So if I call this base, let me use a different color. If I call this base, this would be base and this would be base because they're all congruent. And we know that height in this area chapter is always perpendicular. So if you looked at triangle 2 here, this is a perpendicular, and so we could say that this is height h there. But if we even look at triangle 1, you might recall from earlier examples that it is okay to have a height on the outside of your triangle. So interestingly enough, this height is the same for both triangle 2 and triangle 1. So if I just show you these are the general formulas, what ends up happening is that for triangle 1 in the picture, my area is 1/2 b for base, h for height, which is the same as before, and the other triangle is also 1/2 base times the same height. All of these would cross out, so my ratio would just be 1 to 1. And I'll make sure to do another example like that so you can see another one when the triangles are not similar. Example 3, the ratio of the corresponding sides of two similar triangles is 5 to 2. Find the area of the larger triangle if the smaller triangle has an area of 40. So we're going to need proportions for this, but it tells me that the ratio of the sides is 5 to 2. Because the shapes are similar, I can say that the ratio of my areas is 5 squared is to 2 squared, or 25 is to 4. Now I know that the smaller triangle has an area of 40. So if I think about using this proportion, larger triangle is to smaller, as larger triangle, which I don't know, is to the actual area of the smaller, The reason it works to use 25 over 4 is because this is the ratio of the areas, and this side also has to do with area. So now if I cross multiply, I would get 4x equals 1,000, and if I divide by 4, I would get x is 250, which means that my larger triangle has an area of 250 units squared. Number 4, if the ratio of the areas of two equilateral triangles, aka regular, or equilateral triangles, if you think about it, they have the same sides and the same angles, so they also must be similar. So the ratio of the areas is this. Find the ratio of the sides. Well, because we know the shapes are similar, remember, if the sides are x to y, then the areas would be x squared is to y squared. This time, I gave you this. I told you that the ratio of the areas was 16 to 49. So if we are squaring to get this direction, it would make sense to go this direction to take the square root, which means that the ratio of your sides would have to be 4 is to 7, because what you're technically doing is taking the square root of both. So this would be your answer for number 4. Number 5, which is down here, let me extend this page. If the ratio of the areas of two equilateral triangles, again, it's equal angular and equilateral, so these two shapes must be similar. If this is the ratio of the areas, so I gave you this, I gave you that is 5 to 16. To find the ratio of the sides, just like the last example, we could take the square root of both of them. 5 is not a perfect square, so your ratio would just be root 5 is to 4. And for all of these examples, by the way, guys, you definitely could write it like this instead if you'd prefer. It's your choice. These last examples, what we need to do is decide if the triangles are similar, and we want to find the ratio of the shaded triangle to the ratio of the whole triangle. So if I look at this first example, and I look at the shaded and the whole thing, I notice because these two lines are parallel, I think that's given to you, is that I know that these two angles must be congruent because they're corresponding, and these two angles must be congruent also because they're corresponding, which means that these two triangles are similar because of angle, angle. So if they're similar, I can compare sides first. So the sides from the shaded to the whole would be 4 is to 10, because this entire side is 10, and that would reduce to 2/5. So if the ratio of the sides is 2 over 5, the ratio of your areas, because the two shapes are similar, would have to be 2 squared is to 5 squared, or 4 is to 25. And yes, you could write your answer like this instead. The second example, when I look at it, I look at these two triangles, the shaded and the whole thing, and the only angle that I see in common is this reflexive one. So I would say that these triangles are not similar, which means I need to rely on the formulas to find the area, the shaded triangle to the whole triangle. The area of the shaded triangle would have to be 1/2 base times height. The base of this triangle is 3, but it looks like we don't have a height. So what we could do is drop a perpendicular and recognize that this height is on the outside, but it still does apply to this blue triangle. So 1/2 base times height over 1/2. The base of the bigger triangle is 11, and it has the exact same height, because if you look at the big triangle, it's still the only perpendicular thing you have. So just like a previous example, these two cross out, so your ratio would just be 3 to 11. They are not similar, so I cannot square these. The last example, you are given that these two angles are right, this one and this one. I notice that this angle could be reflexive, so I would say that the blue triangle and the big triangle are similar. So if we want to compare the sides, what we could look for is that this 3 for the blue triangle is between this reflexive angle and the right. So 3 would be to this entire side, which would be 7. So if that's the ratio of the sides, the ratio of the areas would have to be 9 is to 49. final answer.